to talk about how to find different distances between objects in R3. We're going to look at 3 different examples. So in the first example, we want to find the shortest distance from a point to a plane. And this is going to require us to have the plane in Cartesian form. If your plane was not in Cartesian form, you're going to have to put it into Cartesian form. So to do this, let's first take a look at what we might know. So I'm going to put my point in space and label it P. And what we really want to do here is to come up with a good strategy that will work all the time for how to find the distance from a point to a plane. So there's my plane, and the thing that I know about my plane right off the bat is the normal. Because we're in Cartesian form, I see the normal right away. It's 5, -1, 7. And I know that the normal is perpendicular to my plane. Now, if I'm thinking about how would I get from this point, and we want the shortest distance to the plane, we know that that's going to go directly to the plane and meet at a 90-degree angle. And that's going to be very helpful because we know that the normal, of course, is at a 90-degree angle. So I want to find this path through point P that goes and meets the plane at that 90-degree angle. So I know that that's going to involve my point, P, and also the normal. And I want to create this pathway going from P to the plane. And that's actually going to be a line. So I'm going to draw a line kind of farther down through the plane because that's going to go on forever. And there's some point here, and I'm going to call that Q, where that line meets the plane. And this distance between P and Q is what I'm looking for. So we want to kind of plan out our strategy. So first, our process here, the first thing I'm going to do is to use P and the normal to create the equation of a line. Okay. So that is going to get me this black line there, going through P and coming in perpendicular to the plane. Okay. The next thing I need to do is to find that point Q, and that's going to be using our POI skills that we did earlier in this unit. So find the POI of the line and the plane. And then once I get that POI, I've called that Q in my diagram. Now I'm going to find the distance between P and Q, which is the magnitude of vector PQ. So that's step 3. Find the magnitude of vector PQ. So we're going to go through that process with the specific values here so that you have a good example of that. So step 1, remember, is to find the line from point P following the path of the normal. So a line going through this point that's perpendicular to the plane. So my position vector is going to be my point P, and then my direction vector is the normal, 5, -1, 7. So that's my equation of that line. Okay. Step 2 is to find the POI of the line and the plane. So for POI, I've got my equation of my plane, 5x minus y plus 7z minus 109 equals 0. I'm going to want my line equation to be in parametric form. So I'm going to rewrite that as x equals -2 plus 5t, y equals 3 minus t, and z equals -4 plus 7t. So remember back when we did POI with lines and planes, we just took each x and y and z and popped those into the right spots in the Cartesian equation and then solved for t. So that's what I'm going to do here. Running a little bit out of space. Minus 109 equals 0. Kind of really squeezing that in. Okay. So here I've got negative 10 plus 25t minus 3 plus t minus 28 plus 49t minus 109 equals 0. So hopefully I will get some kind of nice numbers here. How many t's do I have? 25 plus 1 plus 49. So I have 75t, and then the number parts, I've got negative 109, minus 3, minus 28, and negative 10. So all those negatives, that's 119, 122. I think that's minus 150 equals 0. And then if we rearrange this, I'll get t equals 2. So I'm going to take this t equals 2 and then find point Q using that t value. So that's negative 2 plus 5 times 2, 3 minus 2 for the y, and negative 4 plus 7 times 2. So point Q is going to be 8, 1, and 10. Okay, so that's point Q. Now I want to find vector PQ. And remember here, we're going to do the end minus the start. So my P is this point here. And Q is the new point that I've found with that POI. So I'm going to do the end minus the start. So I've got 8, take away 8 minus negative 2. So that's 8 plus 2 is 10. 1 minus 3 is negative 2. And 10 minus negative 4 is negative 14. Oh, positive 14. So here, we're going to take the magnitude of PQ as my distance. So that is the distance from point P to that closest point on the plane. And we've got 10 squared plus negative 2 squared plus 14 squared. And 196, I think that's square root of 300. Okay, you can leave that as an exact value. Okay, next example. These are going to get a little bit harder each time. We're still looking at a point, and now we're looking at the distance from a point to a line. So let's again draw a little sketch and make a plan. So there's my point P. I'm going to draw the line that I know here. And from this line, so point P is negative 10, negative 15, negative 7. And the stuff I know on this line is that there's a position vector, negative 3, 1, 2, and a direction vector, which is 1, 3, 7. Okay, so here, the problem with a line and why it's a little bit harder than with a plane is that we don't have a normal to a line in R3. Remember that there's an infinite number of different ways that we could have perpendicular vectors to that direction vector. What we're going to be looking for here is the one specific case where that perpendicular vector comes here. I'm going to call that point Q again. And we get this distance between the point and the line at a 90 degrees. Okay, so the thing that we're going to have to think about here is what we would have to know about point Q. And the most important thing we know about point Q is that it's on this line. So if point Q is on this line here, it's going to have to follow the rules of that equation of the line. And in particular, the x and y and z components are going to have to follow the rules of the parametric equation here. Okay. The other thing we know is that right there, that this is going to have to meet at a 90-degree angle. So what are we going to know about PQ compared to the direction vector of the line? Hopefully, we're thinking if we have a vector here and a perpendicular vector, we know the dot product is 0. So that's what we're going to kind of put together for our plan here. So step 1 is to find point Q. Actually, you know, I'm not going to say find because we're really kind of creating a point. On the line. And we're going to create this point using the parametric equations because we know if the point's on the line, it has to follow the equation rules for that line. Then we're going to find vector PQ. And then we know PQ is perpendicular to the direction. So PQ dot the direction vector equals 0. And then we're going to solve for that point Q. The last step here is to find the magnitude. Once we get Q, it's easy. We just want to find the magnitude of that vector PQ. So that's what we're going to do here using these numbers. So now we're going to kind of take a look. Here's my line. I've got a point P up here, which is that -10, -15, -7, and then I'm going to have some point Q down here. And this is the important thing here is to define point Q because you know it's on the line. So the x value of point Q is going to come from the equation of the line. It's going to be -3 plus t. This is an important skill when looking at lines or looking at planes, being able to define a point on them, knowing that it has to follow those parametric equations. And then for the y, we've got a 1 plus 3t. And then for the z, you have 2 plus 7t. Okay. So now we want to figure out what would vector PQ be. Remember now we're doing the end minus the start. So we're going to take these values minus the starting values. This y value minus the starting y value. And then this y value minus the starting y value. It's important to identify the difference between point Q and vector PQ. Sometimes people mix those up. That's kind of a common error. So -3 plus t, and I'm going to show my work here. I'm doing minus -10. That's my x. Then I have 1 plus 3t minus -15. Of course, you can go right to like making those minus and negatives positive, but I really want to show this and not mix people up with why those are changing sign. Okay. So here, -3 plus t plus 10, I get t plus 7 for my x component. Then my y, I get 3t plus 16. And then the z's, I get 7t plus 9. So this is vector PQ. Now I know that vector PQ has to be perpendicular to the direction vector of the line, which is 1, 3, 7. So here, step 1, remember, was to create your point Q. Step 2 was to find vector PQ. Step 3, we said that's going to be find t by making that dot product equal 0. So I'm going to say t plus 7, 3t plus 16, 7t plus 9, dot, and this is 1, 3, 7 equals 0. And then I'm going to go through and solve for t. So 1 times t plus 7 plus 3 times 3t plus 16 plus 7 times 7t plus 9, whoops, equals 0. And just keep going here. And I think I have organized this so that the t is a nice whole number. I very much hope that I have. I get 59t. So 63, and 48, and 7. Yeah, plus 118 equals 0. So then t is -2. Much nicer when it's not a messy fraction. Now I'm going to find the magnitude of PQ. So if I get the t value, I'm going to use that to find Q. So Q is -3 plus t, so that's -5. 1 plus 3t, so 1 minus 6 is -5 again. And 2 plus 7t, so 2 minus 14 is -12. So now vector PQ is going to be 5, 10, and -12 minus -7, -5. And then the magnitude of PQ is what we're really looking for. That is our distance. So we've got the square root of 5 squared plus 10 squared plus -5 all squared. And then that is root 150. So that's the distance from the point to the line. Okay, one more example we're going to look at, and this is probably the most complicated one. Here we're going to find the difference between skew lines. So remember when we were doing POI, the skew lines were those lines in R3 that were not parallel and also did not cross. So here's two lines. I'm telling you that these are skew lines if I'm looking for the distance between them. We can obviously see that these are not parallel lines because their direction vectors are not scalar multiples. Okay, so we're going to have, kind of drawing this out and thinking about a process, we're going to have two lines like this. On the first line, I'm going to know a point and a direction. On the second line, I'm also going to know a point and a direction, but what I'm going to really be looking for is two particular points where these two lines are closest, and I'm going to call those points P and Q, just like before. And the important thing here is that we're looking for the vector PQ between these two lines, and these are going to meet my lines at a 90-degree angle to each line. So a couple things that you're going to want to kind of make a note of. Point P is on line 1 and Q is on line 2. Now that might seem obvious. Of course it's obvious. I drew them on there. Those are on the line. But what does that mean with the equations? What that means with the equations is that they have to follow the rules. So they have to follow the parametric equations. Okay, so big ideas here. So big idea number 1 is that those are on the line, so they have to follow the rules for the parametric equation. The other big idea is that vector PQ is perpendicular to both lines. So that's going to come in handy as well. So here's the process we're going to do. This one is a little bit longer, so I've just kind of written it out ahead. Create general points P1 and P2. You know what? I find people get a little bit mixed up with those subscripts, so I'm just going to say P and Q. And then we'll call this vector PQ. Just to kind of clarify that P is on L1 and Q is on L2. So we're going to create general points. And this is what you saw in the last example. It's very, very important to be able to recognize if a point is on a line or a point is on a plane, that you need to be able to use the parametric equation to make a general point if you don't know what that point is. Okay, then you're going to come up with two equations from the fact that the dot product with those direction vectors is 0. We're going to use those two equations to figure out our S and our T values. This is more complicated. I'm going to take a look back at this example because unlike the previous examples, we only had one. We just had a T. Now we have two parameters. So we're going to have to do a little bit more work to get these. And then once we find those, we've got our P and Q, and we're going to find the distance between them. So let's go through this. So again, here's our two skew lines, and there's some point Q and some point P, and I'm going to know that PQ, this vector, is perpendicular to both. I know it doesn't look perpendicular, but it's very hard to draw three-dimensional lines on a two-dimensional surface. So I'm going to say that P has to follow the parametric equations for this line. So the x is -4 plus s, like that. -4 plus s. The y is going to be -3 plus 2s. And the z is going to be -2 plus 2s. Then my q has to be the same, but it's going to follow the parametric equations for line 2. So the x is going to be 26 plus 3t. The y is going to be 12 plus 2t. And the z is going to be -22 minus 4t. Now, with how clunky these are and how we've kind of got variables in each, it's going to be a little bit big to find vector PQ, but that's what we're really going to need. So let's find PQ, and remember that we're going to do the end minus the start. This can be a little bit tricky with some double negatives, so try and pay close attention. So I've got 26 plus 3t, that's the ending x value, minus, and I'm going to show some steps here, -4 plus s. That's my x component. Then I have the y component of q, 12 plus 2t, minus -3 plus 2s. And then I have the z component, -22 minus 4t, minus -2 plus 2s. So you have to be super careful with these double negatives. You're going to have to kind of clean this up a little bit. So here for the x, I have 3t minus s plus 30. For the y's, I have 2t minus 2s. And then I have 12 minus -3 is plus 15. And for the z's, I have -4t minus 2s, and then minus, careful with your double negatives, minus 20. So this is going to be really, really important to be able to take this, and then I'm going to know that PQ dot 1, 2, 2, the direction vector of line 1, will equal 0, and also PQ dot 3, 2, -4 also will equal 0. Okay, I'm just going to take a second and try to copy this over to a new slide just to save myself having to write it all out again. My apologies, guys. Here we go. Let's see if this will pop up. There we go. All right, so now this is what I have to do to get two equations, and then those equations are going to have S's and T's, and I'm going to have to do substitution and elimination. So this one is really big. So if I do the dot product of this vector PQ with my first direction, so I'll have 1 times the x value, 3t minus s plus 30, plus 2 times the y value, 2t minus 2s, plus 15, and then plus 2 times the z value, negative 4 minus 2s minus 20 equals 0. So I'm just going to go, whoop, that was 4t. And lots of like terms, these things clean up pretty well. So here I have 3t plus 4t, take away 8t, so I have negative t. How many s's? I've got negative 1s, negative 4s, and negative 4 more, so minus 9s. And I'm just going to move the, no, you know what, I'll just make it equal 0. So then the number part, so I have 30 plus 30 is 60 minus 40, so I get minus 20 equals 0. Okay, so I'm going to take that as equation 1. Then I'm going to do the same exact thing, but dot product the PQ with the second one there, with my second direction vector. So I'm going to say 3, whoops. Pardon me, guys. So I have 3 times the x component plus 2 times the y component, and then minus 4 times the z component, and this should follow the same kind of pattern. So I've got 9t minus 3s plus 90 plus 4t minus 4s plus 30 plus 16t plus 8s plus 80 equals 0. And now I have, let's see, how many t's? I've got 9t plus 4t, so 13, and then plus 16, so I get 29t. Then my s is negative 3s minus 4s is negative 7. Plus 8 is 1 plus s. And then numbers. I have 90 plus 30 plus 80, which I think is 200 equals 0. So now I've got equation number 2. And I'm going to do substitution and elimination. I'm going to see if I can possibly squeeze this in all on this slide. So I'm going to take equation 1 and just rearrange and say that that's t equals negative 9s minus 20. Then I'm going to take equation 2 and sub that in for my t. So 29 times negative 9s minus 20 plus s plus 200, whoops, equals 0. Squeeze that in. So now 29 times -9 is, oh gosh, I should have had a calculator more handy. That is 200 and I think 61s. And then 29 times 20 is 580. And then plus s plus 200 equals 0. Okay. So here we've got negative 260s minus 380 equals 0. My apologies, folks. I have just spotted a mistake in this calculation because I knew that I had made this, that s and t were going to be nice integer values, but I added wrong way back here. So I had 30 plus 30 is 60, take away 40, and I decided that that today was going to be negative 20, but it is not. It is absolutely positive 20. So that then this should have been a positive there as well. And this, my apologies guys, is positive. So that's going to make this positive 580. And then we are going to get much nicer values in here. So 580 plus 200, now we get 780. So s, when we bring that over and divide by 260, we get s equals 3, which is way, way better. Then t is negative 9 times 3 plus 20. So t is negative 7. Much better. It's always those negative sign mistakes. So here we can find point PQ, or we could just find vector PQ. Remember we had vector PQ was, we had that as 3t minus s plus 30 and 2t minus 2s plus 15, and then negative 4t minus 2s minus 20. And we have figured out that s was, make sure I get the right ones here, s was 3 and t was negative 7. So I'm going to plug those in and we're just going to evaluate what vector PQ is. So 3 times negative 7 minus 3 plus 30, 2 times negative 7 minus 2 times 3 plus 15, and negative 4 times negative 7 minus 2 times 3 minus 20. So that gives us, whew, big numbers here. So negative, here negative 21, negative 24 plus 30, we get a 6 for my x component. And here we've got negative 14 minus 6 is negative 20, and then plus 15 is negative 5. And in the z's, we've got positive 28, take away 6, take away 20 is 2. So the magnitude of PQ then is going to be the square root of 6 squared plus negative 5 squared plus 2 squared.
I didn't understand that.
So we get root 65. Whew, that is a big one. That is the biggest kind of distance that you could be asked to do. So those 3 types of questions are really important to understand, and the steps in them. I would say that the main thing that people need to kind of be aware of, watch for these perpendiculars and know that that means the dot product equals 0. Also, the other big idea is that if a point is on a line or on a plane, You should be prepared to write a general equation for that point using those parametric equations, because the fact that it's on the line or on a plane means that it has to follow those rules. And that is it for vectors.